Hello, algebra students. Mr. B here. All right, today we're going to talk about the factor theorem. We know that if we have a polynomial, p of x, and we divide it by the quantity x minus c, where c is some constant, that we get this quantity. We get the quotient, which is a function of x, plus a remainder divided by that divisor x minus c. And what does the factor theorem say? The factor theorem says that if the remainder is 0, then this x minus c is actually a factor of the polynomial p of x. Let's see if we can show that. So let's multiply both sides by this divisor x minus c. We'll do it on both sides. There we go. And on the left side, we see the x minus c cancels, leaving just the polynomial. And then the right side, we have to factor this. We have to distribute this. We get q of x times the quantity x minus c plus the remainder over x minus c times the x minus c. So I've distributed the x minus c. We see that the x minus c cancels in this second term here. And we're left what the textbook calls the division algorithm. The polynomial equals q of x times this x minus c plus the remainder. All right. So the factor theorem says that if this remainder is 0, then x minus c is a factor. And we can clearly see that. If this remainder isn't here, then p of x equals the product, the multiplication of the quotient and this x minus c divisor. Since those are multiplying one another, x minus c is a factor. All right. So what is this good for? We're trying to find all the zeros of a polynomial p of x. And we know that if we could fully factor p of x, it would look something like this. A sub n times x minus c1 and x minus c2, etc., all the way down to an x minus c sub n, where n is the number of zeros there are, and it equals the degree of the polynomial. Like if you have x to the fifth is the highest power, there's going to be 5 of these binomials here, and 5 zeros, c1 through c5. Finding them may not be that easy, but we know that if we divide p of x by these quantities, x minus c, that the remainder will be 0. What we do is we guess what the zeros are going to be and see if the remainder is 0 to show that, yeah, those are zeros. Why don't we illustrate that with an example? All right, here we go. We have a third degree polynomial, so we know there are 3 zeros. And it's asking, is x minus 2 a factor of p of x? So what we want to do is divide p of x by x minus 2 and see if the remainder equals 0. Now we could do this using the, what was it called? The remainder theorem, which said, oh, if you do this division, then the function value at this number will equal the remainder. And we could do that and see if it's 0. But since we're going to be doing this division to try to break down p of x into its factors, we aren't going to really use that method. You could put 2 into this polynomial and see if you get 0. But that's work that wouldn't help us very much in factoring this. It would tell us, yeah, it's a 0. X minus 2 is a factor, but all right. So let's do the division here using synthetic division. I'm writing the coefficients. We know that the c is 2 here. I've made this kind of messy, haven't I? It should say x minus 2, x minus 2. There we go. That's what we're looking for. And we put the 2 here. And let's see what the remainder is. We bring the 1 down. Then we multiply 2 times 1 and put the result here, 2. We add negative 6 plus 2 is negative 4. We multiply 2 times negative 4 is negative 8. Then we add 3 times negative 8. 3 plus negative 8 is negative 5. And, ooh, I'm happy. 2 times negative 5 is negative 10. We add those together in the last column. We get 0. The remainder is 0. Remainder equals 0. So, by the factor theorem, x minus 2 is a factor. And we could write, this is kind of good, p of x is going to equal the quotient, which is given here. This 1 belongs to x cubed, so this one here belongs to x squared. Our quotient is going to be x squared minus 4x minus 5. Remember these? The last row of the synthetic division gives you the quotient. And then the factor x minus 2. Multiplying that quotient will be the polynomial. In fact, we could completely factor because this trinomial that remains is factorable over the integers. What is it? 2 numbers that add to negative 4 and multiply to negative 5. I think that'd be 1 and negative 5, right? And then there's the factor we just found. And so the zeros of p of x are easily seen as negative 1, 5, and 2. These are the numbers that make any of these binomials 0 and would make the polynomial 0. That's why they're called zeros, right? They're the solutions of p of x equals 0. All right. So much for the factor theorem. We'll see you in the next video.